So, we will start where I will pick up from here. Just to recall what I am trying to do in this class is to try and give you a demo of how the project work can be done for the topic that I have, and the topic that I was taking was affordable water for a large scale. So, the methodology was, if you are wanting to come out with a new technology, first you have to study the existing one in detail. So, I gave you a topic of what is the most common practice of meeting drinking water requirements. I gave some 2 methods, source, drawing water. I also covered desalination, and then this table was a summary of this. I am going to spend some time on this table. After the table is prepared, it looks very obvious, but I am going to spend some time how we got into the table first. In the table, what we are saying is, in study anything means you have to first be having some index of what is the state of art at that point of time, what I call as a performance index, which you have to think through and come out with some indices which can capture the essence of what is it at that point of time. It is not a trivial effort, you really have to spend some time, and the sharper you are in your ability, the sharper will be your performance index. So, this is the important thing, and in your project report I will be looking forward for that aspect in great detail. As obvious, if you focus your mind on something, then you will be better able to do that job. If you are diffused, you will not be able to do much. So, in this case the performance index I have taken as what is the investment cost required to set up a plant like that. These 2 questions often comes, how much does it cost? Yesterday lecture also the same, how much does it cost to set up a plant of a certain capacity, how much will it cost to make product out of that plant. These are the 2 things repeatedly come. So, the first one is investment. The units are very clear, it should be in rupees per unit of output, right. So, that should be, because bigger plant will cost more investment, smaller plant will cost less investment, not proportionately less. So, you should have an index which captures the investment to relate to the size of the plant. Here in this case of the water treatment plant, the output of the water treatment plant you can use anything, but conventionally it is written as million liters per day. Why not meter cube per hour? Why not liter per minute? Because usually the end product serves human population, and human population in terms of number of people, and therefore, MLD million liters per day is easy to convert it to a human population. I gave you a number of 120, 150, in some parts of the country even up to 500 liters per day human beings consume water. So, therefore, investment in rupees crores per MLD of plant capacity. So, that is one index I have given here. Regular 2 examples which I gave, one way of doing that, regular water treatment plant. What is regular means? Take a river or a lake, draw water, convert it to potable water, pump it out, about 1 crore per million liters. On the other hand, if the seawater resource osmosis plant has to be made, normally these plants have to be bigger size because they are more expensive. You do not build a tiny seawater reservoir plant. I am coming to that point, very important point, but take it for the minute that what I say is truth. I will prove that it is true. So, normally you build a reasonably big sized plant. There the cost per MLD again comes to 9 crore. So, it is 9 times more expensive to set up a seawater desalination plant as compared to if you are fortunate to have a river or a lake treatment plant. So, that is one performance index. Second is, that is fine, that once off money I put, then how much does it require day in and out for me to spend money on that plant. This is that operating cost, which is unit of measurement is rupees per cubic meter of water is produced. It is not related to capacity any longer. Capacity has an influence of the choice of technology, but once you have chosen day in and out, the technology is not going to change. So, it is just rupees, you are clear about this. This is the key of performance metrics. Here again I gave, in a conventional water treatment plant, it is about 11 rupees, 12 rupees per 1000 liters per meter cube. So, per liter if you see, it is 1 paise, right, 1 paise, 2 paise, 85 rupees from that. Both these costs are, again mind you, when I say, you should always consider what is called as a battery limits, which means where my scope ends. In the case of the water treatment plant, start from the river or lake, ends with the outlet of the plant. The subsequently how it goes to a overhead tank, from there to a community fountain or to individual houses, taps, etc., that is not, because that is so site specific. There will be additional cost involved there, that you should be very clear, because there is a pumping cost at least, plus this laying the pipelines, all sorts of costs are involved, digging, closing roads, whatever. So, this is just only the battery metals plant. That. Then sizes, typically in what sizes these are built, this is again a third performance curve, which means usual water treatment plants I mentioned, it is between 10 MLD to 50 MLD. Why 10 and 50 MLD is because related to the source of the plant. If you had a population and you are looking for a close by water sources, it is a match between the two, right. Nobody wants to take from river Kaveri and feed whole of Tamil Nadu, as simple as that, and same logic is for that. So, this table spend some time. Now, we have got this table, after the table is put it looks honky dory clear, but while you come to that, because this is what is important, if you are now going to think of an additional innovation, the topic was how to create affordable water for a larger population. Now, all we have done is we have done the basic level of what is currently being practiced, we have got performance. If you want to go to the next level of improving on that, unless you have some very detailed about this table, if somebody gives you, you will not be able to, table is a good starting point, but the table alone is not sufficient, it only sets you a benchmark, but unless you knew how the table was arrived at, the logic of how to build better will not come. This is the key point where 95% of technology efforts fail. I am going to come with a practical example. This is true, because people have aspirationally, if this table is given, you can take an aspirational goal and work on this. You know, these days it is so much the rage in go to any jargon, aspirational goals, by 2050 the world will reduce CO2 by 40%. I mean, you could have put 80% also, who the hell cares. What happens for the next 2 years is too much to talk. So, this aspirational in one way it is good, because it is sort of focuses your mind, it motivates you, these are good things in life, but engineers would also have to support that aspirational with hardcore practical knowledge designs. So, the point I am trying to make is, after you derive this performance indices, benchmark of what is the existing one, do spend some time in understanding how we got there, then only you will be able to do a better job of what we can do better. Okay. So, that is what it is. For this I wanted to quickly take you, and you must do the only way to do it, is not big deal, it is just a process, you have to follow the process, you will get it. What is the process is, you have to study the flow diagram and the engineering detail in some depth. This takes time, there is no shortcut, because it takes time you can't do it for a large number of things, your time is limited. So, I will now go through and show you hand sketch, I should show you therefore the flow diagram, right, because I have been talking only blah. So, I will show you some flow diagram. Handwriting is terrible, old man, pardon me. So, that is what it can do. This is the water treatment plant flow diagram, starting from river, it can also be a lake. The difference between the two is the arrangement, how you draw water from that, the detailing differs a lot. In the case of the river, one thing that happens is, ideally the river is flowing, you have to take a channel and take water into that, as simple as that, right. But this channel, if you take it right at some level, after some time, as the seasonally if the river level goes down, the channel from a you can look down the river, but water will not flow. On the other hand, if you really try to make a very deep channel, of course, it adds to the cost. Secondly, lot of sediment, muck, all that will also start flowing in from there. So, it is not a matter we should, this is engineering. So, I have shown here some river, and normally if it is a river, you cut a channel from the banks of the river and take that water, create a mini river kind of a thing, and river surface comes with all sorts of rubbish usually very. So, you put a screen and the screen will filter floating gross objects and it should not get choked. So, you have a continuously travelling grade case. So, this filter it kind of replenishes the surface, it is a very interesting kind of a filter. So, you remove that filter, water comes into a structure, intake structure, raw water. From there it is pumped out, the P1 is the pump, and dotted line is this equipment of intake pump house should be very close to the intake river naturally, because you do not want a river 2 kilometers away and dig a channel does not work. So, invariably this is very close to the river bed, it has got design implications on. Then the water treatment plant is usually where you will locate it is, you will locate it closest to the point of consumption. The reason being pipeline, because after you make the water it has to be reaching all the guys who need it. So, if they are all distributed in this street, that street, there etc., if your water treatment plant is very close by, then the piping requirements will be less, and this is not one massive piping you can put and get away, streets, tapping here lots of complications. So, normally the water treatment plant will be closer to the point of consumption, the intake will be very close to the point of availability, and that is this pipeline. This pipeline length can be anything depending on the survey. Some implication about the capital and the flow diagram, you have to look at it from the point of view. I am telling you a lot of interesting stuff, but pick up only those which has some relevance to those performance matrices, investment cost, operating cost. Then it comes to your storage, you pick up the storage, and from there you pump it out to. Now, at this time all the gross impurities in the water are removed hopefully, but still there will be some amount of small sand, mud, whatever, it is turbid, water will be turbid from the river usually. So, you take that water, you take it to a flash mixture. Flash mixture is just a small high speed stir tank reactor, more or less to say, small residence time, add up something, a chemical called flocculant. These are special substances which can create charge separation in particles, and therefore, the smaller particles will tend to agglomerate. So, you mix that chemical intensively so that it gets distributed, and these are added in 10 ppm levels, parts per million. So, when the water is coming in MLD range, 10 ppm is you have to have thorough mixing, that is the purpose of this flash mixture. So, you mix it up. Now, allow that to settle, so that all these tiny little particles, suspended solids, they just electrostatic attraction join together, become bigger, gravity takes over, settles down. This equipment is the clarifier, this dabba I have shown here. Clarifier nothing but just give lot of space, Stokes settling takes place, bigger particles go down there, and when they go to the bottom, this conical portion, there is a rake that kind of collects it all and then tries to take it to the center of the cone, just separation, solid liquid separation. Clear water overflows, go to another storage. From this storage, still it is not 100% free of suspended solids. Bigger, most of the particles will get separated in a clarifier, but when you want to drink the water, you put it in a glass, you want crystal clear, so to say. So, it has to have a another stage, which is filtration, sand bed filtration, various graded big, small, various particle size of sand is kept, and then it is water is distributed on top of that. It percolates down, as it goes down, all the trace suspended solids are removed, clear water comes out, and it goes to another storage. From that storage through a pump, and you put chlorination at this point of time, because till now what we have removed is suspended solids, that sort of a thing, but it might have some organism, microorganisms from the source, coli, bacteria, virus, whatever it is. So, these have to be killed, therefore, you put chlorine into that pipeline. Why we put at this point of time is because as it enters the customer's distribution pipeline, if you protect it, that is the best protection. Anywhere else you do, over a period of time it can grow. So, chlorination there, after that there is a very specific arrangement, then it goes to the distribution system, which is not in the scope of. Now, this flow diagram, if you look at it, try to relate it to one parameter. First of all, how much does it cost to build? Magic number was 1 crore per 10 MLD. If you now work it out, why it is only 1 crore, why not 5 crores, why not 10 lakhs for example. Actually, in detail engineering we will do all this. Some we will sit and like clarifier I just skipped in 20 seconds. Clarifier design somewhere in mechanical operations or which course you go through. You would have broadly studied about settling velocities, this that, but actually there are a lot of detailed information available. Equipment manufacturers, if you join a company, they will open out and then tell you precisely for this condition, this temperature, this particle size, you have to do some lab analysis test to find out, because you do not know what the particle size you are generating, it varies from case to case. So, there is a detailed methodology of sizing of all this equipment, that is what you will go through, but let us get the feel right now. First of all, you would have noticed now flow diagram completion is after there is a small cheat code. The clarifier bottom I just skipped it, right, it is a solid, then I skipped it off. Actually it will go to a small pit, from that pit it will get, like everywhere water will be collected, including the sand filter, after some time will get choked, because you are adding water from the top, it goes through, you get water, for indefinitely you will not get, after some time there will be blockages. So, you will reverse pump, all that flow diagram will show you. I have shown this tricky line here, this is from the reverse side, you add water at a very high velocity for a short period of time, the whole bed gets churned up, all the particles get out, they also go to this sump and so on. From there it goes to another sand bed, which is like a open construction, sand is filled in a brick vessel, it will percolate. At this point of time the water comes, also can be recovered. Over a period of time this accumulated mud particle sand, you have to scrape it out and remove it. So, that is what is the flow diagram completion. Now, we write out of this equipment list. Land, like we said, we will ignore in this calculation, because government provides free of cost, they acquire the land and give it to you. So, land is 0 value, but you have to recognize there is some land required at 2 places, one near the intake, another place where the water treatment plant is built. Then building, you have to construct a building, that intake pump house cannot just be left to Hava. So, you will have, and if you calculate for 10 MLD equivalent, assume that 24 hours water you can draw. Some people they say you can't draw 24 hours water from the river, local regulation is you are allowed to draw for 12 hours, you can't just continuously draw from the river also, which case for 10 MLD plant your intake pump house has to be 20 MLD equivalent, because half the time. Accordingly, you will size the pump, these pumps will come to for that capacity. If you do the detailed calculations, power requirements will be about 50 to 75 kilowatt. Now, 50 to 75 kilowatt only for the pump, then there will be a room, there will be lighting, the guy is going to sit there, an operator, whatever it is, there will be some space required for him. So, all this building, lighting, path where he has to decently go in and out, access, all that, you calculate, power has to come from somewhere. So, you may find that you have to think of that in mind. So, intake, there will be electrical room at both places to get the power, there will be chemical storage. We just passed 5 ppm and gone, but 5 ppm for a day will not be one bottle, it will be some chemical, and you do not buy every day just in time, morning you order, evening the chemical will land. Now, the chemical probably is made in Baroda somewhere else. So, for a month stock you will buy and keep. So, all that you have to build chemical storage, spares required to run the plant has to be inside a building, lab. Many times these water treatment plants are built slightly away from this population, close to, but not in the thick of, there is a marketplace here, there is a temple here, there are streets here, right now there is a water treatment plant, nobody built. So, it is slightly far away from there, because land is cheaper and whatever it is. So, in which case someone has to work in that plant 24 hours, where this guy is going to live? You can say you come, city buses may not be there in that place. If you expect him, he will come riding in his bike, it is a cost for this guy to come. So, who will come for a job? So, invariably you will find some small amount of residential accommodation you are built, and residential accommodation means it comes along with electrical consumption for them, their own drinking water distribution, their own sewage disposal distribution, whatever it is. So, all that we have to build into that cost. Then I have given you the equipment list, bigger equipment list, piping, valves, electricals, lab equipment, the works. So, if you did this, you will find for 10 MLD it will come to of the order of 1 crore in today's cost. That is how you should, this 1 crore should remember in your mind, right. 80 lakhs, 90 lakhs, do not worry, it just order, it will not come to 3 lakhs, 4 lakhs, it will not come to 20 crores, that is the point. This is very important, you have to go through this, then only technology development will stick in your mind. Otherwise, you can write 3 PhD papers, go ahead and write. If you are really going to be involved in anything useful technology, this detail step painful, have to go through that. Now, of the table 10 crore operating cost I said is 12 rupees, 11.5 rupees, 12 rupees per meter cube. How to estimate that from the flow diagram? Now, you will know most of the equipments written down, where are the pumps written, you will have to know the flow rates of the pump, you will also be able to estimate what is the discharge head required. Good old Fanning's friction factor, you have to know the size of the pipeline, why the size of the pipeline, what is the length of the pipeline, how many bends, lengths, valves you go through, you get it, calculate hydraulic horsepower requirement, then efficiency of the motor and the pump combination, you will get a hang of what is the actual power consumed. This is only for pumps, you have to do that for all electricity consuming equipment, including the light that you provide for that place, etc. It will be a small amount, but you can't forget it. So, if you add up all that, cost it, including the chemicals required, assuming no water cost for drawing from the river, it will come to 11 to 12 rupees per thousand. Now, you have got a hang of why water treatment plants from river and lakes turns out to be probably the cheapest in terms of capital cost and cheapest in terms of operating cost. This is very important to understand this. Now, RO, switch to RO, which is where I said is if it is 1 crore, 9 crore per MLD. So, it is very expensive, 9 times expensive. Now, we have to trigger, show me the flow diagram, why the hell it is 9 times costlier, I mean 8 times, why is it not 20% more expensive, that kind of analysis we are going to do, right. Similarly, 11 rupees per 1000 liters, there I said 85 rupees per 1000 liters, come on, pull out the flow diagram again and say why is it 85 rupees, that is analysis key to do that. Flow diagram again, this time the inlet is from sea. So, I have shown some sea, beach, intake has to be close to the beach, again for obvious reasons you can't take the intake there. This flow here is by gravity, again you put some funny device here, this is the intake arrangement, it has got a small filter, so that all this fish and oysters and whatever they do not land up and come, as much as possible they are filtered. Then this pipeline comes into a deep pit, this pit the flow is by gravity. So, you can imagine if it has to come from the sea, this pit will be a very deep pit, this part is very clear, right, you can't have a shallow pit because water will not flow. How deep, you have to do an actual survey, and also depends on this, is there a regulation where can you draw water, how deep you have to go into the sea to draw water. Obvious things are, if you put very close to the place, there is this waves are coming in creating a havoc anyway, churning out, and so muddy stuff like that. So, you have to take it to some level where it is free from artificial turbidity. So, you have to take, of course, you want to keep it as close as possible, because the longer you take, you can imagine expense, you are laying a pipeline in sea, it is not. Secondly, most of the people, authorities, what they say, you lay a pipeline, you can't just lay a pipeline and leave it like that, you have to bury the pipeline below the sea bed. The sea bed, they say you have to bury your pipeline below the sea bed. So, which means your job is take your pipeline whatever you have designed, dig a trench in the sea, and you can't say, see I am King Canute of Danish, step back, see and waves are stopping, you just have to deal with it and lay the pipeline, and the pipeline should not get tossed up during the heavy cyclonic season. So, there is a hell of a lot of engineering takes place in actually designing and laying, making sure it is safe. So, implication is with respect to capital investment. So, some of that comes from there. Equivalent to our travelling rate, there logs, floating matter, here still some tortoise and fish and all that they land up here. So, you have to catch them and put it back on, then it comes to that and you have a pipe, it goes to the pre-treatment section here. There the treatment was, because it is flowing water most of the time, it is only turbidity that you worry about, you do not worry about rest of it. Here it is, you are taking sea is a living thing. So, apart from high salt, there is a hell of a lot of other stuff inside this. Therefore, the pretreatment section accordingly becomes much more elaborate. You take it here, then first you remove, as usual there will be some turbidity. Obviously, the turbidity in this case is going to be much higher than that of a river or a lake, because the sea is always under churn, right. Actually it is amazing if you go through the detail about what sea. One is always nice to see in the beach and watch the sea on a nice evening or a morning, but actually marine guys who spend their time, they love that. There is so many changes taking place hour to hour in that sea. One of them, for example, is it is reported, Bay of Bengal especially, from the southern part of the country, Bay of Bengal, to the north, there are millions of tons of sand getting transported back and forth because of current, under the current. What if you found there is a seabed here today, marked it with something else, come back and see tomorrow that would have got shifted here or there. So, sand is getting physically shifted, and along with it all the living organisms go. So, this will be turbid. So, you treat this pre-treatment pressure sand filtration. Basically you know this time you can't have gravity because the volumes required are horrendous, that is another point. There I said the water recovery is close to 95-98%, whatever water comes practically lands up. Here with the sea water, the recovery is only about 45%. Why 45, 48, there is a separate topic, but for the present it is not going to be 90, it is not going to be 10, 45%. So, double the quantity of water is passing through the plant for the same output. So, the size of the equipments are becoming bigger. The pre-treatment section therefore cannot have just by gravity and all that, you have to have higher flow rates, and therefore, you have pressurized sand filters, backwash arrangement and all that. Now, it comes to another storage, again you chlorinate it, because this chap like I said has got lot of organics material, they will foul the membranes, RO membranes. So, you chlorinate it. Now, the beauty of RO membranes is if you have organisms it will foul, if you have too much chlorine it will destroy. So, here is something you have to do, you chlorinate it, give some residence time for the organisms to die, then debris you have to remove along with excess chlorine also. So, you have chlorination, dechlorination, funny right, do undo. Then it goes to final cartridge filters, these are micron filters, disposable ones, you can't reuse them. It is like people who have got RO plants at home, you would have found those cartridge filters $400 it costs. Like this, these are cartridge filters you put, they remove the fine particulate matters, everything from there, then this is ready for going to the RO section. This is the thing I am going to talk about, some energy recovery business in that. Before that, look at RO is very simple, you take water, all this pre-treated clean water, pressurize it to the osmotic pressure and above that, so that across the membrane diffusion will take place. What you get out is called permeate, which is clean water containing probably 200 ppm of salts. When you start with sea water is 35 to 38,000 ppm of salt. From 38,000 ppm you have landed up in permeate 45% of the water containing 200 ppm of salts you have got. Accordingly, the other portion 55% has got enriched, got reject. So, that is it, it happens in a membrane setup. Membrane itself is a beautiful thing to see, but I will skip, for details are not very important. We have to go back and say you said 1 crore per MLT and you said 9 crore per MLT, you said 11 rupees per meter cube, you said 68, come on show me the flow diagram. So, that is the discussion. So, let us keep the nice bit for it. So, this happens. Here the key point is this pressure is very high, that is where maximum energy consumption takes place. Even though water is incompressible, it consumes energy to compress water like that, and there is a pressure drop across this membranes also. So, this is the big time water. So, when look at it carefully, this is coming at high pressure, goes through the membrane, this flows through the membrane and comes out, permeate, which means it is through the membranes, this pressure will be low. If this is typically 70 bar for sea water, this will be about 3, this will be close to 65, because reject is not flowing through the membrane, it is flowing across the membrane. As it is flowing across, only water molecules are diffusing going through. So, this is quite rich in terms of salts, as well as it is still maintains fairly high pressure, there is a pressure drop of course. So, clear this point. Now that is energy, right, any pressurized fluid is energy. Now I will go back to talk about this hero. This is a beauty of engineers. What they have found out is, if you recall Mettur dam or whatever dam where there is olden days power used to be extracted, idea was you build up the water pressure, then allow that water to flow through some turbine, and the potential energy of the water is getting converted to kinetic energy and then power. Some clever guy thought this is high pressure water, it is as if it is stored in, if it is 65 bar means 650 meters tank, I have stored that water, you got to do something to recover the power from there. Beautifully they devised a device which is compact. Later on you Google through it is called EDX, energy recovery device, you can Google through that. Basically it is like very cleverly designed device, it has got two parts. Like that, you put high pressure water, like I said 65 bar, as it goes through that it rotates the internal elements because potential energy to kinetic energy and comes out at a fairly low pressure 5 bars. Now the feed which was going to the RO, it has to go from all this cleaned up water, chlorinated, dechlorinated business, that fellow comes in the opposite direction, picks up that energy. So there is an, actually it is a energy exchanger, like heat exchanger, thermal energy is exchanged between a hot fluid and a cold fluid. This is an energy exchanger where the energy from a high pressure stream of liquid is getting transferred to a low pressure stream, it goes in and this becomes to that extent pressurized. Therefore, it is still will not be equivalent to the RO feed pressure, because this anyway is coming in at 65, you can't have it higher than that, same delta T equivalent, delta P equivalent here. But then the duty of the RO feed pump comes down to that extent. This one device has reduced the energy consumption of RO plants quite substantially, so that today in that number I gave 4 units of electrical energy per 1000 liters of product water, that has happened because of this device. If you remove this device, it will increase to 7 or 8. So almost 50% of the energy recovery has come through this clever device. Then there is the permeate water that comes out is 250 ppm, it is actually good, but it will be slightly acidic because of it. So you remineralize it, just take limestone treatment, just allow it to pass through a limestone bed, it will pick up a little bit of calcium, because the calcium magnesium completely gets removed in the RO plant. To some extent it is required, a little bit of calcium and magnesium is required. You saw that IS 10500 water specification, it specifies some maximum, but 0 is not accepted. So there is some remineralization, storage, again chlorination, pump it out to wherever it is. Reject comes in their water treatment plant, happy situation of reject does not exist, because most of the water comes here and there, only 2% evaporate water. Here 55% of the water is to be sent back somewhere else. So you take it to your tank, lay one more pipeline back into the sea. Now this is again complication. If the intake is coming from there, if I put this reject also close to that place, okay, sea is sea, but nevertheless there is some complication, if not no after some time, right. So if that is there, this you have to put it, look at the sea, most of the time in this direction current, underwater current, not surface, that do some study, find a place and put it, and through a something called a diffuser, which means it is a final end pipe which will not put it at one point, it will put it like that and take the whole thing, put it into the sea. Our fellows are standing, bury it please, and diffuser cannot be buried, by the way, pipeline can be buried, take permission and there is some special cage made, the diffuser is not there, and put it out. Now with this, point of doing all this exercise was, why is it more expensive? If the benchmark of water treatment plant conventional is 1 crore MLD 11 rupees, now I ask you to think this context, why seawater RO plants are more expensive 9 times and water cost is also approximately 8 times, because first of all the ability of equipment to handle water is twice, because only 45% recovery. So if there you had some size of equipment for the same capacity, you are having double the size of the equipment. So, it increases the cost at least twice, you can assume. Secondly, that is river water, nice clean fellow, most of the times it is carbon steel, cast iron, that material, simple material of constructions work. Sea water, this is corrosive, like quite corrosive. So, very expensive material of constructions are required, that increases the cost sharply. So, two factors for cost increase. Then the treatment required, pre-treatment required is very elaborate, because it is also coming from, so that adds up to the capital cost and so on. So, that is why finally it lands up at 8 to 9 times more expensive. That is also the reason why the operating cost instead of 11-12 rupees is coming to 85 rupees. Okay. So, this is the understanding I gave for us to take this table and then say, when somebody gives you a performance metric of an existing situation, one thing is to just take it and keep it in mind. Second is, if you are serious about developing technology, operating, making a difference, etc., from a engineer's point of view, you got to get back and get this feel, visualize existing process in this situation. So, you will get to know, aha, compared to that, this capital cost, compared to, you do not have to, of course, you have to at some point of time really work out the details, because nobody will say approximately and all that will not work, like yesterday our speaker spoke, but that is detailing. As initial stage of your career, you must develop this feel, this is very important, and this is a lifelong skill. Okay. Now, I have another 5 minutes, so I will go through and say why I brought this topic is, what next? We have gone through if off balance I will continue in Monday's class also, but just here I want to give the background to this. So, what all we have done till now is we have taken an example of case study of water, understood this existing methodology in some detail, also applied our mind to know why they are like that, the way they are, and even then there are small improvements opportunities you will notice, but now we are shifting our gaze technology development. You know, we want to, what is the topic is affordable water for humanity. Now you have seen so many popular and scientific publications will come, all claiming to make that big breakthrough which will make humanity less dependent on water and all. I have taken 2 of them, again no harm to the authors, because after all they were motivated with a different understanding. My motivation I am trying to give, and that is not the only motivation, is if you are going to work in industry where you have to pay and you have to be paid, you got to take that reality into account. So, with that in mind, 2-3 examples, I will not go into detail, I will do it on Monday, but 2-3 examples. One is something called solar thermal energy will be used as a, this is often you will hear about. Suddenly somebody comes and says, we are wanting to use solar energy, you have to think, okay, what is the solar? So, this is one effort at solar thermal energy. Government of India funded this in Ramanathapuram, some district, because Ramanathapuram is a district where in Tamil Nadu down south it is little stress for water. So, this project was set up saying that objective as claimed by the project authorities is develop solar based desalination water. If they had stopped there, I have no problem, it is just one of those, but if they are saying this is something going to solve the problem of water availability, affordable for large population, in that context only I will comment. Okay. As an idea, any idea is a good idea. So, we will spend some time in the next class on this, we will analyze it. The second one I will take is, someone came out with something called Surya Jal, using sun energy to create water. So, what is it? Again I will analyze it with respect to the goal of that. And third, this you must have all heard about Vayu Jal. This is the latest. You are worried about water? From air you can draw water, what is the problem? So, these 3 technologies we are going to spend some time. Again idea is, do not get me wrong, my tone will be harsh, critical, not because I have no respect for that idea, I respect all ideas, But I take a view, if I am true to the concept of people have to be provided with water for large number of people, then my performance criteria is not superiority of technology, innovative ideas, the brilliance of the mind that worked on this. This is, I am not discounting, I am not taking it, my choice. I am taking performance metric as cost per MLD, what size of the plant can I build, what is the operating cost. Now one may argue these are bullshit. I mean, what is this? When you are trying to get with great ideas in life, you can't come back and say that what is the cost of this. I quite agree that in some scientific ideas you can't immediately start asking what is the cost, but I am not talking about scientific ideas here. Here the claim is I want to deliver water to a large number of people at a low cost. Then I am game, I can take a very harsh view, I will take the view in the next class and go through. Keep that in mind, 1 crore per MLD, 9 crore per MLD, 12 rupees per 1000 liters, 85 rupees per 1000 liters, and again what we will do, we will take that idea, what the idea is. Only method is go through the flow diagram, figure it out, how much will it cost, how much will it cost to operate. Okay, that is what we will do in the next class, Monday. Monday class Professor Nagarajan also will join. After this part I will take about 20 minutes to close this. So with that, this demonstration example project is over. We will spend time in listening to you what is the groups have chosen the topic, because Monday class we really have to freeze the topic of that. Then only you will have sufficient time with all your other commitments to be able to do reasonable justice to the project work. If you delay it any further, then you will be unnecessarily under a lot of stress towards the end. It will show in the quality of the submission, it is not recommended. So at least you can, after all topic is only one of interest. Guideline is do not choose too ambitious a topic, because then it is a hard struggle. Choose something which is simpler, because it is not the ideas we are discussing, it is your methodology of given an idea in a limited context of an industrial career, how are we going to go through. So it is a very modest objective. So choose also something which is modest just for practice. Okay. That is what we will do on Monday's class. Thank you.